Alright, hell yeah. So, a viewer sent me this problem. It's in Mechanics of Materials. This is Hibbeler. And wanted me to go over free body diagrams. I just did about a 2-hour, probably longer intro to material mechanics. So watch that. I'm probably going to post this first though. So, free body diagrams, I don't know, I feel pretty good about them because I have this method that is just like, hey, cut something out and then put it in outer space. In outer space, things just kind of float around. So if I put something in outer space, and it's kind of taking something and having it in two locations. One, it's on Earth, so this is going to be Earth, and then outer space. So let's just take this spring. So the spring in outer space is just this spring. That's it. And but then I go, and it's just floating there. You know what I mean? Ain't no thing. Now, this will be good because the first thing that you should probably do is pick a mass, and then I'm going. So this thing's hanging from like something. This is hanging from this I-beam. So what I'm going to do is I'm going to have an I-beam, and then I'm just going to say a mass is being hung. So let's do the free body diagram. So what I would do is I would chop that mass out. So I'm gonna do this. I'm gonna chop this whole thing out, and then have this floating in outer space. And I'm just gonna have this be represented as m. So this is outer space. I'm going to have a chunk of mass. In outer space, it just floats there. Now, back on Earth, if this is mass, there's an Earth underneath us, and we know that there's a force of gravity due to the gravitational constant, the mass of this block, times the mass of the Earth, divided by the distance from the center of the Earth to the center of that block. For all intensive purposes, that is just the radius of the Earth. You could be on top of Everest or down in a pit, and is about the same as the radius of the Earth. You know what I mean? So anyway, so that's the radius of the Earth, and we have to square that. So cool. So on Earth, we have a force on this mass, and what we know. So now cool. So now on outer space, we're going to put a force due to gravity on this mass. And it doesn't have to be due to gravity. We just know that we're going to apply a force. And that could be the same thing as having this mass float in outer space. And then I came up with this idea. Is you put a little lightweight rocket cone and then a tube of fuel. And you light this. And so that's going to apply a force that makes this thing travel that way, right? You know what I mean? It's going to be a force. There's going to be a force on this mass that's going to push it that way. You have a force on the mass. And we know that F equals ma. You know, who cares? But we just know that if you have a force on a mass, and that's it, you know, like this, it's going to move in that direction. And let's say this was stationary. It's not only going to move in that direction, it means that it went from stationary to changing its velocity. And that's the definition of acceleration. If you have a force, you're going to change the velocity of that mass. And that's going to constantly change every second. Change in velocity per change in time. Okay, so, but then we got to come back to Earth. And is this thing just traveling that way? Like if we dropped it, it would be, but it's not. So visually, we know that this thing is not traveling that way. So there has to be a force up. Like there has to be another rocket cone that someone turned on that has a tube of fuel going to it. You know what I mean? And that's why you can have this tube of fuel for statics problems, because if you just had one force, well, hell yeah, this whole mass is going to go that way, and this tube of fuel has to probably catch up. But for statics problems, hell yeah, this mass is just floating in outer space. I'm going to light this rocket, and I'm going to light this rocket, and both of them are just going to blast, you know what I mean, do their thing. This rocket is going to put a downward force. We're going to call that the force of gravity. This has to be a force, we're just going to call it F for now, and that counteracts that. And the reason we have to have this is because we see that this chunk of mass is not moving in that direction. It's not moving in that direction. It's not moving in the cardinal directions. So we say at, you know, the velocity is 0 at time 0, and then we wait about 5 seconds, and then, hey, it hasn't moved. So we know it's stationary, but we still know it's made of mass, and we still know the Earth is underneath it. And so we still, you know, the free body diagram is like, hey, this whole mechanism is still it's still a mass in outer space from the free body diagram perspective. And I know there's going to be a force this way, you know, equivalent to gravity, and but I observe that it's not moving that way. So there has to be an equal force, something that's equal to the force of gravity, that's not the force of gravity, you know what I mean, but it's just equal to, and we have to figure out what the hell that is. And for this problem, it is just the fact that it's, you know, hanging out right there, kind of gripped onto something that, for all intents and purposes, like ain't going nowhere. And so, hell yeah. So that's where that force is. So, yeah, this I-beam is kind of fascinating. Acts as this rocket. This I-beam is applying an upward force, just equal to this downward force. You know what I mean? Because that's kind of the funny thing about, you know what I mean, if you have like a cantilever and you're just like, I'm just hanging out on, oh man, oop. Sometimes my pictures get crazy. Alright, so anyway, so I was just imagining someone hanging on this cantilever. Oh, that's even worse. Anyway, why aren't they flying upward? You know, I mean, we know there's a force of gravity down on them. Well, it's because, like, hey, this cantilever just matches the force of gravity. How does it do that? You know what I mean? That comes up a hell of a lot, especially with friction and stuff. But, hell yeah. So that's, and I don't know. They call this the normal force, which sucks, because N is a horrible letter, maybe, for a force. You know what I mean? Because force is, I don't know. You could go F of N, but it's the normal force. Yeah, I think it's a dumb name. But yeah, that's going to be the normal force. But it actually is this I-beam applying an upward force on this mass. Alright, hell yeah. So that's the first one to do, is just kind of the mass of the entire thing. Now this problem I was going to simplify, even though we know that this rod is a hell of a stiff spring. So you can actually, any material mechanics problems, you can just turn that into a spring-looking thing. But we're just going to neglect that. And we're going to say that this pipe of water is filled with water. I should mention what the hell this problem is. And that we have 2 stainless steel rods. We should read it though, because I don't know what material this is. A spring-supported pipe hanger. So this is the pipe. This is the pipe. This is the hanger. 2 springs. When they're unstretched, or they were unstretched. Yeah, even so, the pipe is negligible weight, but once it's got water in there, it's hella heavy. The spring constants are 60,000 newtons per meter. We're probably not gonna. Hey, we're gonna do 1/10 of a meter though. Okay, so this is about 1/10. So sometimes you can kind of just, you know. So it's gonna be a 1/10 of 60,000. That's gonna be 6,000 newtons. So we're gonna have 6,000 newtons in both of. And so I'm just going to say, hey, they're both displaced. So we're going to have a force of 6,000 newtons in both of these. So just right off the bat, it's like, well, hell yeah, 12,000 newtons. You know what I mean? So that's the idea of like, keep it simple. And yeah, sure. Yeah, this is going to stretch out. And is that, and now the question is, does that mean that this is heavier or is it lighter? I guess it would be heavier, I would imagine. I don't know. Yeah. Okay, so, and then we have 3 stainless steel rods. We have A to B, C to D, which have a diameter of 5 millimeters, and then E to F, which has a diameter of 12 millimeters. And then we have a rigid beam, GH. Oh, I never knew it was a beam. Yeah, so if the pipe is displaced 82 millimeters, when it is filled with fluid, determine the weight of the fluid. Holy hell. So I need to see where this actually falls, because it's just like, how much do you do? You know what I mean? Because are you going to figure out the displacement of the beam itself? You know, if we pull on this beam, the beam's going to shape like that, right? Because you're pulling up right there, and then you're pulling down right there. So that could be some deflection. And then the springs for sure have a deflection of the spring. So I'm going to say the deflection of the beam. And but hell yeah, you know what I mean? If it was just the springs, we're just like one and done. And we just said this was 100, you know, a tenth of a meter. And we just got on with life. But hey, that's pretty decent, you know what I mean? And that would be the weight of the pipe, the weight of the water in the pipe. Okay, so the other thing that happens is that you're going to have a force on the spring. So let's, the spring, so the free body diagram of the spring looks like this, unstretched, just chilling. But now it is going to be crunched in, and we're going to have 2 opposing forces, the forces on the spring. So that's a free body diagram of the spring. And, oh, it's interesting, you know what I mean? It's just like, why couldn't I draw this free body diagram like this? Like, because it's pushing, you know what I mean, against the rod and stuff. This rod. Alright, hell yeah. This is probably where I'm the worst at free body diagrams. So I can for sure know that this spring was unstretched. I can float it into outer space using my method. And then I can visually see, like on Earth, the 2 different things in material mechanics. I can either know the load that's being applied to something. So if this is the spring, maybe I know the load that's being squished on that spring. Or I can just know that it used to look like this and now it looks like this. And so I know a force like this had to be applied. So that's how I know that 2 opposing forces had to squish this spring. They have to be equal to each other, because this spring isn't traveling any direction in this way across the universe when I float it in outer space. So this spring, free body diagram, is just like floating it in outer space and then being able to apply those forces. And I don't know, yeah, you could just throw the rockets on it. In this case, you would, to get this force, you would have to, yeah, that would work. And then to get that force, you would do that. And then you would have your fuel system. Cool. Now let's take this, we can take this pipe right here. So if I take this pipe, it has a lot of weight in it, so it's got mass and mass. It's got a force due to gravity of all the water in this. And so we're going to float that in outer space. And then we're going to apply that force of gravity. Well, same thing we just talked about. It's not traveling this way, so we have to have something, you know, doing this on it. and then keeping it stationary. And those are going to happen right there and right there due to symmetry. I'm just going to say those are the same, so we have the force of gravity divided by 2. And so, sweet. And this force of gravity is going to be the weight times... It's just going to be the weight. Sorry about that. Yeah, the force of gravity is just the weight. It's going to be the mass times the gravitational constant. So if we knew it's mass, but yeah, we just want to work in weight. So that's going to be the force. So this is W divided by 2. There's a free body diagram for that, kind of fast. Alright, so now let's take one of these rods. Let's see what happens. Right here, we're going to have a force down. So yeah, okay, so the rod's just floating in outer space. And then we go back to Earth and be like, well, is there any forces on it? Is there anything like doing stuff to this rod? Like, is anything is anything touching this rod? And hell yeah, this is touching the rod. And, you know, you could do the free body diagrams on both. Alright, booyah. So, yeah, let's see if I can figure this out. So we have weight over 2. Okay, so if that's touching the rod, and then this beam is not touching the rod. You know what I mean? It is free to float through that rigid beam GH. Okay, so the only other thing, and then this spring isn't touching the rod. This spring right here is not touching the rod on the bottom. But this spring, and then this rod has some nuts on it. I'm just going to include that with the rod. But hell yeah, this spring is actually applying an upward force, and I'm just going to say that's circular around there. And I can just put a resultant from that spring. So we have the force of the spring, and we can see that the force of the spring is W divided by 2. So hell yeah. So now we're just working, you know, we're working from here into some more complicated stuff, I guess. Cool. Oh, and the crazy thing is, let's see. So this pipe is going to be, yeah. So they say the springs are, this problem sucks. Because the fact that they say the springs are originally unstretched. Like, are they saying the springs are unstretched? Yeah, see, this problem could get as heady as you want. Like, are we going to say that this pipe has weight? We don't need to. We can say the water in the pipe plus the metal pipe and the flanges connected to the pipe is just W. Like, that's what we want to solve for. And therefore, W2 is on these rods. But then, guess what happens to these rods? These rods also have a weight of the rod, which is the mass of the rod times G, you know, due to the gravitational constant. Or due to the Newton's law of gravitation. And so the force on the spring is going to be W divided by 2 plus the weight of the rod itself. And that is going to be the force on the spring. You know what I mean? So if you want to get technical, hell yeah. Like this is made of mass. We have mass here. And that's where you would do an integral. You know what I mean? I kind of want to do that. I don't want to do that right now. You do a volume integral. You say, hey, it has a density, and then we have a dV, and then we're going to integrate over the height and whatever. No one wants to do that. But there you go. So that is more techy, is that, hey, these stainless steel rods have some weight. Now, we could see if it even makes sense to do, I don't know, you know what I mean? If our initial guess was just 12,000 just from the springs, like one check on reality was like, well, how much does all this stuff weigh? But it doesn't even tell you the weight of GH. It doesn't give you any information on that rigid beam. It doesn't give you a moment of inertia. And so all you would need was the material moment of, well, you don't even need, yeah, do you need the material properties? I think you just need the moment of inertia. of that beam, which they don't give. So we can't figure out deflections in the beam. So we're just going to assume the deflections in the beam are totally negligible. We're just going to assume that there is extra deflection in these rods, these 3 rods. So that's where this problem is going to be. Cool. All right, so we did that. So now we have the force in the spring. And so we know the force in the spring, like right there, like this force in the spring. So we know that force and that force in the spring. Okay, so now let's do the this GH. And like I said, these rods aren't touching. You know, so that's for the free body diagram. We're going to float this in outer space, and then we want to know what's touching it. Or if it has mass itself and there's an earth underneath us. But we're going to say this is a massless rod, I guess. Massless beam. And we have the springs. The springs are actually touching it. So we have the force of the springs. Cool. And we have both of them. So we have 2 times the force of the springs. And then anything else touching it? Hell yeah. This is that. So we have the force of the big rod. We're going to call that capital R. That's just 2 times force of the springs. And the force of the springs was the weight of the weight of one of these rods. The force in one spring is the weight of this rod plus half the weight of the water. Cool. Now, the force in this is going to be 2 of the force in the springs, which is going to be the weight of the water plus 2 times the weight of the rods. And that would make sense. The weight of the water plus 2 times the weight of the rods. Alright, hell yeah. So we're back. Let's grab a fresh sheet of paper, because all this stuff has weight to it. So I'm going to say this is W. I'm going to say, come out here, and I'm going to say this is the weight of the rod. I'm even going to come here and say this is the weight of the spring. And then I'm going to come here and say this is the weight of capital R, the larger rod. And we should have a weight right here of the weight of the beam. And all of those... and it's even fascinating, like from like in the introduction, I said if you had 2 steel molecules, you know, some sort of distance away, that from a change in length perspective, they could only, you know, change in length so much before you would get them to break. And that's going to be the force that you can apply on a couple chunks of steel. And that relates to material mechanics, that you can change something in its length, so we have a max change in length. And what you're going to get is a pressure, and that's going to be max stress. So you get a pressure that develops and a change in length. Both of those, you can measure one or the other, and they're linear, they're synonymous with each other. And you could do half the max, half this change in length, and you'd be just gravy. But then these both values, you'd have half the pressure, and you would witness half the change in length. So I just mentioned this because if we take this larger rod, I'm not going to do it in this video, but I need to make more videos, and they should do integrals, just basic calculus. But we have a, you know, you would take a little volume right there, and so we would have a little volume, and this has a weight density, and so the actual weight, dW, is going to be dV times the weight density. So weight density is, let's say it's going to be a force, like a force density. And do you use this for force density? This is mass density and this is weight density. Yeah, I think I'm doing it right. So this is going to be newtons per meter cubed, and then their volume is going to be in meters cubed. How you would do that, just with, you would say that this is going to be a force divided by a length cubed, and then a volume is going to be length cubed. And then you would yield force out of here. And that force is going to be your weight. And the only, and then this is even not fully explaining the fact that you have Newton's law of gravitation, because hey, you do have a distance, maybe you call it r, because the force of gravity is gravitational constant, mass, that little dm, and so yeah, and if this is weight density, how do you get mass density? Isn't that force is mass times acceleration. If I had a weight, is a mass times g, and so if I was trying to get, so if I had a little change in weight and a change in mass, g, and if I was trying to solve for dm, dm would be dwg, and then dw, so dm would be dv rho, whatever that is. I forget what that one is. I mean, I shouldn't, but anyway, gamma, dv gamma divided by g, that's going to be dm. Cool. So now, like, even if we say that we have a little chunk of dm right there, which is dv gamma g, and really dm should be just dv rho, because it should be irrelevant. Mass should be irrelevant of what your gravitational, what planet you're on. And so cool. So you have a differential mass right here, a differential volume, and a mass density. And Newton's force of gravity, which we're going to say dF of g, is going to be gmme divided by radius of the Earth squared. So this is going to be gravitational constant, dm, mass of the Earth is constant, and then the distance. I'm just going to say, let's say this is the y direction, this is the x direction. I'm just going to say that's y squared. And so, and now the force due to this thing, and we said that dm is dv rho, and dv is dx dy dz. And so that gives us the triple integral. So if I wanted to know the actual force of this thing, I would go to the center of the Earth, have that be 0, x and y, and then this would be the radius of the Earth plus elevation, and this would be, anyway, so yeah, it's kind of a, but it's good to every once in a while do this type of stuff, because now to get the force of gravity on this rod, we're going to take the integral of g, this is going to be dx dy dz, mass of the Earth divided by y squared. So hell yeah. So when we integrate and we're going to have a triple integral in the x and the y and the z range. And when we integrate the y range, hell yeah, we're going to get something a little trickier. When we integrate the dx, well, that's just going to be like this, the radius of this diameter of the rod, or negative radius to positive radius. That's going to be the x direction. The z direction is going to be the length of the rod. But no. What's the z direction? If we have x, y, z direction is going to be this way. Oh yeah, z direction is also, yeah, we have something round here, and so we would have to use an equation. Yeah, you would have to do the equation of a circle. So your x and z ranges, you would use polar coordinates. So you use polar coordinates for x and z. You'd do cylindrical coordinates. Yeah, so now I get that. You know what I mean? Because you're not doing a square or a rectangle. And so yep, you would use polar coordinates for your x and z axis, or cylindrical coordinates. Radial coordinates for x and z, and then height would be your y. Yeah, that's probably brutal. Anyway, I have no idea like how much they actually, like we got our first answer of 12,000 newtons. Yeah, so now I guess what I'm going to assume is that the only three things that are going to change in length are these two rods and this bigger rod. That's it. I'm going to say there's no deflection in this rigid beam. You know, it's sufficiently rigid, and it's also sufficiently light. And so I'm going to say there's no mass. Yeah, that's kind of a bummer with this problem. Oh, yeah. So the whole reason why we did that is because the force is going to be additive. So like what do I mean by this? If I just have a, you know, something welded to the ceiling, and it's a heavy steel bar, and I'm gonna say it's we're gonna divvy this up. Let's say we just divvy it up 10 times, and this is 1,000 millimeters, and this is 1,000 millimeters, and so we have 10 meters of length. And then what are we going to assume? Let's say that I just assume that this this chunk right here, 1 meter, that's going to be 40 inches, and about 10 pounds. I'm just going to say it's about 10 pounds. Cool, and I'm going to say the cross-sectional area is 1. So I'm just going to say, like right here, I'm going to get a pressure of 10 psi. So that means like right here, I'm going to get a pressure of 20 psi. And let's say I just kept on doing this. You know, every meter weighed 10 pounds. And this was actually 5,800 meters. You know what I mean? And then right at the top, I would get 58,000 pounds per square inch, and this would break. So this is where you can't even have a steel cable long enough to go to the bottom of you know, the deepest part of the ocean. Yeah, I don't think you're able to. No, you just have to make it thick as hell. No, it doesn't matter. It doesn't matter because the actual weight of the cable itself is strong enough to break it. Yes, that's fascinating. But that's what's happening. That's what's happening at even this level, is that the pressure, the pressures will be differential throughout this, because this has a weight. I I mean, so basically we have this rod, and we're going to, for just all intents and purposes, have the weight of the water on it. And then what we say is that this rod at the center has weight. So just weight of the rod. So then right up here we just say, hey, the force normal to actually hold all this has to be the weight of the rod plus the weight of the everything. We're just going to call that the water. But hell yeah, so that force is going to be the weight of the water plus actually the weight of the rod. But it's a bummer when we talk about elongation because yeah, let's do this one. And even this one, we're not doing it as an integral. We would have to divvy this up into dx slices to infinity. But we're just going to take a 10-meter rod and divvy it up 10 times. And we're just going to say that in general, in this first meter, we're going to have 10 pounds. And we know it's 1 square inch. And we know if there is 58,000 psi, we're going to have a change in length of 0.002, or if we have this, sorry, I should say this correctly. If we have 58,000 psi in this little chunk, it's going to have a strain of 0.002, which is 0.002 is equal to change in length divided by the initial length. And so that means we can find the change in length by taking the initial length times 0.002. And we're going to say this is 1,000. So that change in length is going to be 2 millimeters, if that was the case. Now, we have only 10 pounds. And so we don't know what our strain is. But we know that, so we have 10 pounds per inch squared. Oh, yeah. So then you can use this relationship. That strain is modulus of elasticity, which is just a constant times strain. And you got force divided by area. E is change in length divided by length. And we're going to say, hey, we do have a pressure of 10 psi, pounds per inch squared. And this is going to be 29,000 times change in length divided by this this length of, and we have to keep this in so I'm just going to say these are 40 inches because that's a meter. So I'm going to say this is 40 inch. That's our initial length. And we want to know our change in length. Okay, so we're just going to do 10 times 40 divided by 29,000. Cool. So our change in length is going to be 0.014 inches. So not much. And let's do the last one. If we thought on the last one, we would have a psi of 100 pounds per square inch. Our change in length would just be 0.14 inches. Cool. So that's if this thing weighed 100 pounds, and it was 400 inches long, because that would be 10 meters, basically. It would stretch well, that last little chunk would stretch 0.14. The first one would stretch that. So I'm just going to say they average, if it is linear, 0.07 times 10. So we got 0.7 inches. Ooh, I feel like that's probably not right at all. But if this is 400 inches, like 100 divided by 58,000 times I'm going to try to talk my way through this. So let's say the average stress is just halfway. So it's going to be 50 pounds per inch squared. That's going to be this. We want to find the strain. So I'm going to take 50 divided by 29 million. And that's going to, and then multiply by the initial length. So times 400 inches. And that's going to give me the change in length. So the change in length is imperceptible. It's 0.006 inches. And that's what we would expect. Just do the weight of something. The weight of something isn't going to change. The displacement's not going to be very much. Just due to its own weight. Now, if you load up a member, hell yeah. So you could have a member that only weighs, let's say, 10 pounds. But you have a cross-sectional area of 1 square inch, so I can put 58,000 pounds on that. You know what I mean? So something only weighs 10, and I can put a force of 58,000. Well, just know that if it's hanging, this is 58,000 plus the 10-pound weight that it actually is. So the force normal to actually hold this thing up is 58,010 pounds. All right, hell yeah. So I think for this problem, I would neglect. I'd probably neglect the weight of everything except the water. All right, hell yeah. So I think I'm going to be done with this part. We kind of went over free body diagrams, and now I'm going to try to solve this problem. You know what I mean? From neglecting some things and then adding them in, and let's see how we do.